Any questions about anything coming up? If we do? Okay, so we're almost done with 6.5, which is basically where the test 1 material ends. We'll get a little bit into 6.6, but I do want to leave. Basically, we'll kind of cut it partway through so we can. I really want to leave most of Monday for y'all to ask me questions about the test and the review stuff that I showed you. So when we wrapped up last time, we were talking about Simpson's rule, and basically the way it is structured. So this pattern of coefficients that looks like it alternates, but it's a little, in a subtle way, is a little more complicated than that. But basically, those coefficients of 1, 4, and 2 populate or are multiplied by all these different sample points, depending on how many intervals you want to divide your integral into. Any questions about the way this is structured before we apply it? Okay, so I'm going to stick with the function that we have been dealing with. And we're going to use Simpson's rule to approximate this. So I forgot to write it down, but we're going to basically approximate it using all the same parameters. So same integral, same number of subintervals, which is 4. But now from there, we have to set up Simpson's rule to help approximate that. So what is that going to look like? So first thing, I'm going to multiply this by all of my sample points, delta x over 3, right? And then what's the first term on the inside of this bracket?
So f of the initial.
Right. So for now, I'll just call it x naught. We'll figure out what the x values are. Something I encouraged last time was basically work from the outside in. So I know the first term will have a coefficient of 1, right? The second term, or sorry, the last term will have a coefficient of 1, so f of x 4. And then what's the coefficient on the next pair of terms inward? So 4 f of x1, 4 f of x3, and then what's left? Is it just x2? Okay, so what's the coefficient on x2? So 2 times f of x2. So here's our skeleton of the way we're going to set this up. What is the delta x for our situation? Why is it 0.5?
2 minus 0 divided by 4.
Right, so that comes from how long the interval is. So basically, with the difference between my upper bound of my integral and my lower bound, so that's 2 divided by the number of intervals I want to do, that's 4. So 1/2 divided by 3. Now, let's make a little scratch work here. So we have 5 sample points. And I think we said last time that the number of sample points you have is always going to be 1 greater than the number of subintervals you're taking. Sure, so the 0.5 comes from this. So b minus a, that's part of it, over n. So yeah, and whether or not you remembered, I'm almost positive that you've all probably saw this formula like when you went into integration at the very tail end of Calc 1, if you took it here. So understanding based on how long the interval is that you're trying to find the area underneath the curve, and then you divide that up evenly among however many subintervals there are. So that'll give you that change in x.
So it's 4 minus 2 over, or 2 minus 2 over 4.
Yeah. So yeah, 2 minus 0 over 4.
So why is it over 4?
That is baked into Simpson's rule.
Oh,
So the
oh
yeah, so the delta x itself is 0.5.
Yeah.
So Simpson's rule has that it divides it by 3. So yeah, the delta x itself is 0.5. Simpson's rule cuts that down 2 1/3. All right. I want 5 sample points. What are they? 0. What's the next one? 0.8. Oh, I think you're a step ahead of me. I'm good. I want the X values right now.
Oh, 0.5.
Right. So is it a coincidence that these two things are exactly a delta X apart? No. So that's that would be, I think, probably the easiest way to figure out where your sample points are. The first sample point will be the lower bound of your integral. The final sample point will be the upper bound of your integral. And then delta X is just this linear pattern that I'm going to tack on a delta X to get from one to the next. All right. I believe we have all this information, right? F of 0, F of 0. So let's just go to the formula. What is F of 0?
0.
Okay. What is F of 0.5? 0.8 plus 2 times F of 1, which is, it's 1, plus 4 times F of 1.5, which is,
0.923.
I know there was a 0.923 and a 0.8.
Yeah, 0.
Is that the last one? Okay, plus 0.8. So I believe that's everything. Someone double check that I didn't swap these two values. I don't think I did. No. Okay. All right. So any questions about the way we populated this, the way we filled in all the values? If we're okay with that, can I get a final result? If someone beats me to it, yeah. I'm getting 1.615-ish. Unless I did it wrong and someone gets something different. But that feels in line with the other things we've gotten. Okay, so any questions about the way we built this, the way it works? Okay, so that's basically all the approximation methods that I'm going to require of you for the test and for the homework and stuff. So we did basically 3 different methods, left, right, and midpoint, that all involve finding the areas of rectangles. We did the trapezoid approach and now Simpson's rule, which is not really dealing with areas at all. It's something a little different. So let's do this now. Let's see if those are any good. Can we find this integral without doing approximate methods? U substitution, what's a good U? 1 plus x squared, what's du? 2x dx. Okay. Oh, so let's write this out first. So this is the integral of, is this simply du over u? Cool. From 0 to 2? And then what? Okay. So that's something I was waiting for. I was wanting to see if we remembered this. So a couple ways to go here. I either need to keep these bounds, I need to make sure I know that those bounds are x values. And redo the substitution, or you can do this. I can make this the integral of du over u with some new bounds. What would those new bounds be? 1 to 5. How'd you get 1 and 5?
0 for x. equation and 2 for x in the u equation.
Yep. So yeah, based on the u that Pia gave us, we can get new u values. So those are both fine. Those will get us to the same place. So the natural log of u from 5 to 1, or 1 to 5. So this comes out to be what? The natural log of 5 minus the natural log of 1. So exact value is natural log of 5, right? If we approximate, so let's see how good any of our estimates were. .609. So I mean, a lot of these were close to this. Some of them were a little further away, but I think Simpsons was probably closest, right? It's not to say it's the best. It was the best in this case, but the situation will depend on which one's the best. Okay.
So can you use Simpson's rule to check your answers kind of if you have time for that?
What do you mean by check your answers?
Like if you're doing a definition integral and you want to check to see like, or is it just a completely different method to use?
No, I mean it's so Simpson's method. So Simpson's rule is not ever going to give you. I mean, not ever, but it's not going to be an exact thing, because even though this was the closest for us, it's still taking this function, which is never constant. Yeah, always changing, and I'm taking only 5 points from it. So because I'm doing that, I'm going to introduce some error. This just happened to be the one that introduced the least error. But here's the thing. Let's say we did the exact value first and we got 1.609. And we're pretty confident with that number. And then Simpson's rule gave us something that was close to 5. That should set off alarms that something went wrong somewhere. Because like there's always going to be some error involved, but there should be some kind of fidelity between your approximate answers and your exact ones. Good question. Anything else about any of the techniques we did here? Okay, one thing I want to briefly talk about before we put this topic away is there are some applied things that you'll be asked to do on the web work and maybe on the test that sort of look like this. So applied meaning there's a context given to them. So this graph shows traffic on a Wi-Fi network. Do we know what this stands for? It's important. It's bits. So close. Megabits per second. So on a certain day. So basically t equals 0 represents midnight. T equals 24 represents midnight the next day. And then that rate in megabits per second is on the y-axis there. So it peaks around 7.5, it looks like. So what would the area under this curve give us? So without us trying to approximate it, let's talk about what the area underneath this curve would actually tell us. Any thoughts? Total traffic in 24 hours. Okay, so total traffic. What would you measure that in? Like, what's a good unit for that?
Some kind of time.
Okay, so let's talk about this. We don't have a unit on the y-axis. What's a good unit for the y-axis just in our graph? So maybe I'm not being clear enough. That is measured in megabits per second. Okay.
That over hours per second.
Okay. So you're saying the total traffic would be megabits per second over hours, or something like that. How do we feel about that? Here's one problem we probably need to talk about. Time is obviously part of this, right? But on one scale, we're talking about time in seconds. On the other scale, we're talking about time in hours. Is there something we could do to? So we have a choice. We can talk about this in terms, we can talk about the rate in megabits per hour, or we can talk about the time in seconds. Which one would you like to do? Time in seconds? So how would we convert this time scale to seconds? Multiply by 60, is that enough? I think by 60 squared, right? So yeah, so 60 seconds, I'm sorry, 60 minutes times 60 seconds. So that'll do it. So that'll greatly amplify all these hour values. But now let's do this. So let's stick with rectangles. That's one of the things we talked about. If I were to find the area of this rectangle, let's actually find a number for it. What would the area of this rectangle be? What's that?
24.
24? How'd you get that?
3 times 8.
3 times 8. Okay, so let's be clear about the units. 3 what times 8 what?
3 hours times 8 minutes per second.
3 hours times 8 megabits per second. Something we did decide is we're not going to say 3 hours. We're going to say the number of seconds that I ate. So 10,800 seconds times 8 megabits per second, which comes out to 86,400. 86,400 what? Simply megabits, right? So we took the rate of megabits per second and multiplied it by the number of seconds that elapsed, and that gave us the number of, so 86,400 times a million, that many bits. So we just did that for one rectangle, and I picked that one because the height looked pretty constant over that subinterval. Any questions about how we built that up? So the area is something, yes, I know you can do numerically. The bigger thing I want to focus on, because I think that this is the thing we added on to all the things we've already been doing. Are we okay with why this final answer is a megabit value as opposed to a rate or a time? If we're good with that, how might I find this? So it's asking for could I find out how many megabits were transferred on this network in that entire day? How would I do that? I could use Simpson's rule. Is that the only way I can do it? I mean, so any of the things I showed you, we could do. So something you'll see on the web work that if you haven't already gone and look at it is, so all the examples we did, like we kept the same function, the same interval for every single thing, and we got different numbers, right? So in order for us to, basically because of that, we have to prescribe what method to use. If I ask you for a Riemann sum, I better tell you if it's left, right, or center points. I also better tell you how many intervals to use, or else all those final results are going to come out slightly different from each other. So yeah, be aware of what specifically, like what the conditions are and how that's going to change. Any questions on this section before we walk away from it?
So for this one, you will not give us a function. You will just
Yeah, I mean, so, yeah, so I mean, yeah, so all the examples we did before this last one, I gave you the algebraic definition of the function, right? And like I drew some graphs, but I don't actually know what this curve looks like. I haven't thought about it. The graphs I drew were basically to organize kind of what we were doing. As opposed to this last one, I have no idea what the algebraic definition of that function is, but I do know basically I can get some x and y values from that graph. So yeah, be ready to handle this both ways. And really, let's look at the way Simpson's rule is set up. Like I don't need to know what the function's like formula, what its algebraic definition is to make that work. I just need to know some values on that function. So if you can pluck them from a graph, you can get the information that way. Good question. What else? Okay, so like I said, that covers basically what the test might ask you about. We got about a half an hour left. Let's dive into section 6.6 for a while. So this section's about something called improper integrations. So why is it called that? So let's build up to that with an example that kind of starts with stuff that you have done. So I want to evaluate this integral for a lot of different values. So this t, basically I want to do the same function and integrate it with the same lower bound, but I'm going to vary what that upper bound is. So before I do that, I'm going to draw on the margin here a picture of what this graph looks like. So 1 over x squared looks something like this. We've got a vertical asymptote at the y-axis, and as x gets bigger, we get closer and closer and closer to the y-axis, right? So vertical asymptote at the y-axis, horizontal asymptote at the x-axis. All these integrals are going to begin at, let's say that's y equals 1, x equals 1. So basically, the left-hand side of all these areas I'm going to find are going to be here. So the first area I want to find is from 1 to 2. Is that an integral you know how to do? So what is the integral from 1 to 2 of 1 over x squared dx? So the antiderivative of 1 over x squared is negative 1 over x. From 1 to 2 is negative 1/2 minus negative 1, which is positive 1/2, right? So the area under that little segment right there is a half. We okay with that so far? So that's stuff you've done for a while. So now what I want to do is this. Basically what I'm going to do is I'm going to move that right wall. We're going to move it slowly to the right until finally, basically the last thing there, we're going to remove that wall. See if we can find the area of this thing that we allow to be infinitely long. So now what if I add this area onto it? So what do we expect to happen to the integral now? Should get bigger, right? So now the integral from 1 to 10 of 1 over x squared dx. Same antiderivative, right? Negative 1 over x. So if I evaluate this at 1 and 10, what happens? So negative 1/10 minus negative 1 is 9 over 10. So we're getting numbers for these because the area I'm finding, this shape is how at its tallest, how tall is it? Like what's the height at its highest? No, so the height, so vertically, the vertical height. So the shape that not the infinite case that we're working up to, but the 1 to 10 case. That is how tall at its tallest point. One, right? So on the left end, when x equals 1, y equals 1. So I have a height of 1. So I have a finite height. How long is it? 10. So still, at this case, it's 10 units long. So because of that, it's finitely tall, it's finitely long. It should have an area that I can figure out, right? Will that be true if I remove the right-hand wall in here and just take all the area? So now it still has a finite height of 1, but now the length of this thing is going to be immeasurable, right? So what do we think is going to happen there? So I don't want to treat infinity like a number. So one thing I'm going to do differently is this. I'm going to set up a limit as t goes to infinity of the integral from 1 to t of 1 over x squared dx. So this is something that's a little different from what we've done before. Usually or probably always, the integrals we've done have been on upper and lower bounds that are numbers. They're real numbers. This time we can't really do that because we want to do infinity. We can't treat infinity like it's a number. So we're gonna have to bring in this limit. But a lot of the ways we do integrals and a lot of ways we can think about them are going to remain unchanged. When you integrate something, when you take a definite integral, what's the first thing you have to do? I still need the antiderivative, which is still -1 over x, right? I don't want to forget my limit operator. The limit as t goes to infinity of what? -1 over x from 1 to t. So now that I've taken the antiderivative, what do I do with that antiderivative to think about the integral? So I want to evaluate this new function at the upper bound, so -1 over t, and at the lower bound, -1 over 1, and subtract them. So now I have the limit of this thing. So basically, aside from the fact that I'm writing this limit operator at every step, we're basically doing the same thing as we're used to. Find the antiderivative, apply the antiderivative evaluate the antiderivative at both bounds. So now I have this limit expression, -1 over t plus 1. That comes out to 1. We okay with that? So in this case, we have this, if we think about it in terms of an area, I made this shape that is infinitely long. But even though it has infinite length, it has a finite area. It has an area of exactly 1. Go ahead.
Will we be able to just do like the last part that you did where you found the limit, or will we always have to test it with...
No, so the reason I had those other values in there is to show that we are building up to that. So what we didn't do is evaluate this at 100 and 1,000, but let's fill in those blanks here. So our first case was a half, right? Then 9/10. The integral from 1 to 100. 1 over x dx is 99 over 100. And the integral from 1 to 1,000 is 999 over 1,000. So basically, because as I can make so if I do want to make this thing finitely long, I can get as close to 1 as I want for the final area. But if I just let it go infinitely long, I get an area of exactly 1. But no, this was a means to building up to that. I'm not going to make you do this every time. Anything else about this first one? Okay. So how about this one? I want to integrate from 1 to infinity of 1 over x. So how do I begin? So I'm going to set my limit operator. That's like symbolically speaking, the biggest new thing we're adding. So I'm going to use that limit to rewrite this integral from 1 to t of 1 over x dx. From there, what do I do? So yeah, find the antiderivative, which is natural log of the absolute value of x. And something I always forget to do, carry this operator. So the limit as t approaches infinity of the natural log of the absolute value of x from 1 to t. And then
So would you always put your bounds at 1 and 2, or would you put infinities on the?
well, I mean, this and this are equivalent things. But here's the problem here. Let's say we handle this integral like normal, then what would I do? This would be the natural log of x from 1 to infinity. Okay, does that equal the natural log of infinity minus the natural log of 1? So this is a little bit, not a little bit, this is illegal because now I'm treating infinity like it's a number.
Yeah.
So that's what we're trying to stay away from, is this kind of, yeah, basically abusing infinity. Yeah, it is not a real number. We can't really, in a lot of cases you would get away with it, but not always. So I'm trying to steer into this limit operator. So knowing that the antiderivative of 1 over x is natural log of x, natural log of absolute value of x, what do I do with these bounds now? So the limit as t approaches infinity of the natural log of t, I'm going to drop the absolute values because we're not dealing with anything negative. Natural log of t minus natural log of 1. Any thoughts on what this is going to do? So I'll rewrite one more time because I know the natural log of 1 is 0. What happens to the natural log of t as natural log of t, or sorry, as t gets very, very big, what happens to the natural log of it? That's right, I cannot, it's not ever going to stop increasing. It's going to grow without bound. So therefore, this integral diverges. So what does that mean? Maybe not a word you've heard in a math context before, but basically, this is probably the first time any of you have seen an integral that fails to give you, or sorry, first time you've seen a definite integral that fails to deliver a real number. So now that we're dealing with these intervals that are infinitely long, that's a possibility now. So we've seen one example where we got a finite number, right? So if this integral diverges, what do we call it when we get a real number? That converges. So these are pretty standard terms you'll see for integrals like this. And the reason you haven't seen it is because every single definite integral we've talked about converges until now. Now you have to account for the fact that they might not. Question?
I was just saying, like, the past example of convergence. So this one would be convergent just because we got 1.
Yeah.
And no infinity.
Right. So if your definite integral yields a real number, it converges. If it does anything else, it diverges. So you're kind of a long way from it, but the first way you talk about integrals is Riemann sums. And not just Riemann sums, but what happens when you take the number of rectangles and make that number of rectangles infinitely large, right? I want to divide my area up into, divide my length into this infinite number of rectangles, which you can't do because you can't have an infinite number of rectangles, but you can use limits to think about what might happen if the number of rectangles just kept getting larger and larger and larger. So if that limit doesn't exist, which is really what happened here in example 2, if that limit doesn't exist, we have divergence. How are we doing so far? Okay. Let's go again. Oh, so let's try to say something in general here. So we want to talk about this integral here, the integral from 1 to infinity of 1 over x to the p. And I want to know for what values of p does the integral converge. So what do we know so far? Where did we see it converge and where did we see it diverge? So at p equals 2, it converged, right? What happened to p equals 1? Because that's what our last example was, right? The power on x is 1. What happened at that power of x? Diverge, right? So basically, one thing I want to show you here is, do we know what the graphs for 1 over x squared and 1 over x look like? So I think I drew the graph as 1 over x squared as something like this, right? Yeah, it's not drastic enough. What does the graph of 1 over x look like? At least on the positive side of the y-axis. Do we remember? Really, it looks very similar. It has a vertical asymptote at the y-axis, and it, decays like this, right? So because of those graphs, maybe it might seem strange that one of them diverges, one of them converges, because they both kind of have that same behavior where it starts as this vertical asymptote of the y-axis. It always decreases and gets closer and closer to the x-axis, but 1 over x does not decay fast enough because the integral is going to be infinite. 1 over x squared decreases fast enough to actually have to get a result for your integral. So can we form a guess about what 1 over x cubed would do? That is going to converge because that function is going to decrease even faster. So I'm going to bold in all the things that converge. We know that 2 and greater converges, right? Because that was the first example we did. And we knew that one converges. So yeah, I picked 1 and 2 because those are the ones that we've specifically looked at. But what do we think happens in the middle? Oh, by the way, let's talk about over here. If 1 over x diverged, then 1 over like x to the 1/2 is going to diverge for the same reason. So basically what we're trying to figure out what's going on here is things strictly between 1 and 2. What do you think would happen if my power was 3/2? Any guesses? You think it would converge? Let's find out. So hold that thought. I'm not going to test 3/2 because I don't want to test all these points. Let's do this instead. I'm going to leave the t. I'm going to leave the p generic. The limit as t goes to infinity of 1 to t of 1 over x to the p dx. What is the integral of 1 over x to the p? It might seem weird to have a generic thing there, right?
-1 over x to the p plus 1.
Let's do one more thing here to make this easier to think, maybe easier to think about. Let's call this x to the negative p. How do you integrate x to the negative p?
Divided by negative p plus one, or multiplied by one over negative p plus one, and then it's x to the negative.
Well, you have to do something to the exponent first, right?
You have to add one,
So I add 1 to that. So negative p plus 1.
then negative p.
So that's your antiderivative, right? So I like what Caleb said. The natural log is the thing that messed this up, right? What do I want the power on x to be? To make sure that the integral, this new thing right here will diverge, or this new thing will converge. That's it. It's got to be greater than 1. Like, I don't care how much greater than 1 it is. So basically, this thing will converge for p greater than 1. So we saw that it failed at p equals 1. It will converge for any p larger than that, no matter by how small. It just has to be a little bit larger than 1. Questions? Go ahead.
I'm a little confused. Why is it p greater than one?
So let's keep applying this limit here. So are you good with this antiderivative? Can you see my cursor? So x to the negative p plus 1. So now what do we do with this? Let's put the t in there. So the limit as t approaches infinity of x to the negative t plus 1 over negative t plus 1. What happens when I put 1 in there? X to the negative 1 plus 1, so that's x to the 0 over 0. No, negative p plus 1. Oh, I'm plugging the wrong things. So I integrated x, right? Which means I did this wrong too. Let me try again. So t to the negative p plus 1 over negative p plus 1 minus 1 to the negative p plus 1 over negative p plus 1. So let's clean this up a little bit. What is 1 to the negative p plus 1? Yeah, 1 to the power of anything is 1. So what do I get here? T to the negative p plus 1 minus 1 over negative p plus 1. So let's talk about this limit here. I have 2 different letters in this thing right here, right? But which one of these things is actually a variable as far as I want it to be? It's actually not p. It's just t, right? So that limit operator is letting t get bigger and bigger, right? Is that okay? Or do I need to try again explaining that? So the limit here is t, which means basically is this. I want to let t get bigger and bigger and bigger, right? One thing I want to do here, I think I need to move upward. So let's do some clumsy migration. If I factor out a negative, what do I get? I get t to the negative p minus 1 over negative p plus 1. What happens when I raise something to a negative exponent? Well, so I can rewrite it, right? 1 over t to the p minus 1 over negative p plus 1. Okay, so I didn't write the limited thing here. Let me just abbreviate. So first of all, before I say any more, are we okay with how I got to this place. If you're not, please stop me, because I did a lot of manipulation and kind of jumped around on this page a lot. But if this is the limit I'm looking at, so now I'm going to let t go to infinity. So as I let t go to infinity, I want this numerator not to get really large, right? So what kinds of powers are going to make this 1 over t part of it actually get smaller? For example, if p was a half, then I would have 1 over t to the negative 1/2, right? So let's actually write that out. If p is equal to 1/2, then this becomes 1 over t to the negative 1/2. Agreed? Is that the same as the square root of t? What happens to the square root of t if t gets really, really big? It will increase without being bounded. So, but what instead if we do p equals 1.1? What happens here? This becomes 1 over t to the negative 1.1. No, it doesn't. I'm sorry. Because we said p minus 1, right? This becomes 1 over t to the negative 0.1, which is the same as t to the positive 0.1. What happens to t?
So.
I feel like I'm doing something wrong. Yeah, I am.
So what you want is, if we look at the limit, that p, like in the bottom, this is t minus p plus 1.
Mhm.
You basically you don't want that to be 0, right? You want it to be.
I want it to be strictly positive.
Right,
So the fact that I want p minus 1 to be positive, which is the same as saying I want p to be at least 1. That's what I was trying to build up, and I made a bunch of missteps. So now I have 1 over t to the 0.1. Now let's look at that. What happens to 1 over t to the 0.1? Or maybe let's break it down even smaller. What happens to t to the 0.1 as t gets really, really big? It gets really, really big, right? But if I divide 1 by that thing that's getting really, really big, that goes to 0. So that's why that's the boundary line. I need to have p be anything larger than 1, and I get convergence out of this. So a long, rocky journey all the way to this. This is the punchline. So basically, if I have integrals that look like this, you can know that convergence will come if p is greater than 1 and diverge in any other condition. Any more questions there? Okay. So we're not going to do this one right now, but what do you think about this? Converge or diverge? Should converge, right? So we'll talk about that more at a later date. So lots of review stuff on Canvas. Make sure you look over that. And then we will talk on Monday, do some review.